The question that I have is, could you describe the method of joins? Alright, let's first set our goal for the analysis of a truss. In general, our goals would be to determine the values of the support reaction and the member forces. There are two methods of analysis. One of them is the method of joins, which is the subject of this video. The second one is what is called the method of section. So let's talk about the method of join. We kind of touched on this already a little bit, right? In the method of joins, we analyze join by join and solve for the unknown. So this method is not unlike what we did in the case of cable systems. So let's go through some guidelines here. We start from a join that has at most two unknowns. This is due to the fact that we can only write down at most two equilibrium equations per joint, right? These are the force equilibrium equation in the x direction and the force equilibrium equation in the y direction. So how come we don't use the moment equilibrium equation? Well, a joint is like a particle, a point, right? All of the forces acting at a joint acts at a point, and therefore all of the lines of action of the forces pass through the same point, and therefore the moment equilibrium equation is trivially satisfied. Referring to this example truss, joint A, right, when we start has more than two unknowns. We have an unknown on this member, we have an unknown on this member, we have two support reactions, AX and AY. And therefore, we won't be able to start analyzing that joint right away. So only way to analyze that joint is to first find the support reactions AX and AY. In many cases, this is what we need to do. So we find the support reactions first by considering the entire truss. We can write down three equilibrium equations for the whole truss. Remember, in this course, we are only going to consider statically determinate trusses, right? So the number of unknowns will not exceed the number of equations we can write down. So you can write down three equations, there are three unknowns, and we should be able to solve for the three unknowns. So that becomes the first step in method of joins in many cases. In some cases, however, you might find a join that has just two unknowns, and therefore you can start from there. So once we identify the join that we want to start with, we want to isolate the join from the rest of the structure and then draw a free body diagram for it. In isolating the join from the remaining structure, you need to section the members that are connected to that joint. You mark and label those internal forces. Remember, in a truss, the internal forces on members could either be tensions or compression, but I recommend that you mark them as tension to begin with. The values we get for these forces at the end will tell you whether they are actually tensions or compressions, right? In completing the free body diagram, you want to mark all of the known and unknown forces. Here's an example of the free body diagram for joint A. Make sure your free body diagram has all that is needed. You have all of the forces marked and labeled, including the arrows indicating the directions of these forces. If you have inclined members like AC here, you want to define their direction properly. So once you do, you can write down the equilibrium equation just by looking at this free body diagram. You don't have to go to the main structure to do that. In the analysis of a truss like this, I recommend that you keep doing this separately outside of the main structure in order to avoid confusions. Your third step is to write down the equilibrium equations as needed and solve for the unknowns. Here I say as needed because in some cases you may have a joint with just one unknown and therefore you only need one equation to solve for that unknown. But in general, you have the two force equations available to you. Some of the forces in the x direction should be equal to 0. Some of the forces in the y direction should be equal to 0. So generally, you'll write down the two equations and then figure out a way to solve for the unknowns in these two equations, right? But in some cases, you might find that one of those equations will only have one unknown in that equation. Like for example, assuming these support reactions are known, right? equation number 2 only has one unknown, FAC. So if I started with that, I could find FAC right away without having to wait for the other equation, right? So these are some minor practical considerations, and you might find that sequencing the equations in this way, on this basis, kind of makes the analysis flow a little bit easier. So once you're done with a joint, you move to one of its neighbors. And of course, you want to move to a neighbor which has at most two unknowns. In this example, joint D is one of those neighbors. We already found the force on member AD, and therefore there are only two members with unknown forces. We can write down two equilibrium equations at that joint, and therefore we can solve for these two forces. This member CD, however, as we will discuss in another video, is what we call a zero force member. In other words, without going through an analysis, we can predict that the force on that member is zero. So when we start on a new truss, this is one of the first things we do. We go through the truss and identify members where the forces are zero. In other words, we identify the zero force members in the truss. So there's no need to try to find the forces on those members. We already know that the forces are zeros. But this is a special case, of course. It's not always true that the force on member CD is zero, but in this case it is. So we repeat this process going from joint to joint until the forces on members that we are interested in are found. This method is what is called the method of joints.